So now let's review again things that probably you have seen in the past, but it's never hurts to review it. Let's see what kind of intermolecular interactions we have. If we have intermolecular interactions, it implies something. It implies that we have molecules. So it's not an ionic solid, it's not metallic, it's not a covalent molecule. Intermolecular interactions only take place when you have molecules. So what kind of interactions are we going to have when we have molecules? The very famous hydrogen bond. When does the hydrogen bond take place? It takes place when your molecule has either fluorine hydrogen, nitrogen hydrogen, or oxygen hydrogen. The fact that you have a very polarized bond towards the very electronegative, but also that hydrogen is so light, it creates that hydrogen behaves pretty much like a quantum particle, so it's able to build a very specific kind of a dipole with a neighbor molecule that is particularly strong. Okay, something that you're already familiar with, the dipole-dipole interaction. When your molecule, in here you have acetone has a dipole pointing this way. The molecules, when they have a dipole, they will be placed in a way that the negative arrow is pointing to the positive arrow. Okay, that's the dipole-dipole interaction. Not when you have pure substances, but when you have mixture. For example, when you can throw salt in water, you will have a specific kind of intermolecular interaction that is very strong, and that's the so-called ion dipole. You have an ion that interacts directly with a dipole. Notice it doesn't have to be a hydrogen bond kind of dipole. Okay, and I tell you ahead of time that this is actually stronger than hydrogen bonds. This is why we throw salt in winter in Minnesota, because salt can melt the ice, because this type of interaction can break the structure of the ice, because this type of interaction is stronger than hydrogen bonds. But we'll go back to it to make sure that we understand it. So, and the last one, and that's important to understand, the last one is called dispersion force, also known as London forces. London forces. It takes place in all molecules. In all molecules. So do not disregard this as something that happens only in the nonpolar. It happens also in the polar molecules, just that the polar molecules have a dipole-dipole interaction that typically is more important than the London forces. So what is this London force, aka dispersion force? Well, it's what we call an instantaneous dipole. All molecules, all atoms have an electron cloud. So if this electron cloud at some point were to move towards one direction, it would create an instantaneous dipole. The fact that it creates an instantaneous dipole, this will create, if you will, kind of a chain reaction. What you have here is 3 atoms of helium. Helium, of course, doesn't have a dipole, and yet helium at the solid state, the atoms of helium interact with each other. And how do they interact? Through only dispersion forces. The dispersion forces, as we said, is this instantaneous dipole that induces the dipole in the other atom's neighbor to it. So this will be very weak, but it definitely holds the atom together for a certain amount of energy. Okay, so let's see how these different interactions rank. Well, you just need to look at the boiling point to see which one is stronger. Because we have water and salt. Once we throw water in salt, the boiling point increases. This means that the water of molecules now are held together. This was the ion dipole kind of interaction. Water is a hydrogen bond, and it has 1 degree less. Isopropyl alcohol, again, it has hydrogen bond, but it's not able to build the 2 hydrogen bonds that water can, so it'll have a lower boiling point. Acetone, this is a dipole-dipole. Diethyl ether, if you remember what diethyl ether is, 1, 2, 3, 4. 1, 2, 3, 4. Notice oxygen here has a certain dipole. Okay, so this is not linear. It means that ethers will have a tiny dipole. Diethyl ether is a type of dipole-dipole, but smaller than acetone because you do not have the sp2 carbon that can create a larger kind of dipole. And finally, methane and argon are what we call London or dispersion. So here you have already the rank, and this is the rank. The rank is, as you go up in this table, the stronger the interaction is because the boiling temperature is higher. Notice also that another factor that we can use to describe is the enthalpy of vaporization. They are almost directly related. We will talk about one day that there's an entropy factor in there that is not the same. This is mostly energetic, this is all combined, but they are very much related. So that means that the higher the boiling point, the higher the enthalpy of vaporization. In other words, the energy needed to vaporize, in this case, 1 mole of that substance. Okay, so what happens when you have mixtures? What kind of intermolecular interactions do you have? Are they different at all? Or, well, we will see that in these cases you can have new kinds of intermolecular interactions. You don't have to memorize them all, but you will see that hopefully it makes some sense to at least acknowledge them. The ion dipole, we already talked about them. That's when we throw salt in on the snow to melt it. Another kind is when you have hydrogen bond among two different molecules that can offer hydrogen bond. The dipole-dipole can also be present among two molecules that have dipole-dipole interactions, even though those are two different molecules. And now let's see. Once you have like a chloride and hexane, you have an ion-induced dipole. What is that? Well, this is charged, so this will be able to polarize a little bit this molecule. Okay, this will be weaker than if you have, for example, up here an ion dipole, but nevertheless it's a kind of intermolecular interaction. Also, the same way that we have ion-induced dipole, we have a dipole-induced dipole. So for example, the dipole of water can induce a dipole in a nonpolar molecule, in this case in an atom, which of course is nonpolar. Okay, and finally dispersion that we are already familiar with. Okay, so you will see very often this kind of graph, and it's just for you to memorize a little bit that these are the hydrogen bonds. What you're seeing here is the boiling point or the boiling temperature of hydrides. And notice that if you go from left to right in the periodic table, you go from top to bottom in the periodic table, like in top to bottom, okay, you go in this direction, top to bottom, the mass is increasing. You're seeing that the higher the mass, the higher the boiling point, provided that you don't have a different kind of interaction. This is showing that hydrogen bonds override the factor of the mass, and it takes place only when you have nitrogen, fluorine, or oxygen. Notice that methane, because you have carbon, this is not a hydrogen bond. Okay, and therefore it has a lower boiling point. Anyhow, this is what we already said. Okay, we already ranked the strength of the different intermolecular forces, and we have to also acknowledge something, is that, as we said, the higher the mass, provided that the rest of the variables is the same, the higher the boiling point. Okay, and also the linear branch spherical, the more linear your molecule is, the higher the boiling point. So how can we explain these two things? Well, hopefully it makes some sense that the higher the mass, the more energy it takes to vaporize that molecule, because after all you're working against gravity to go from liquid to gas. So think of this mostly as a gravitational effect. However, the linearity, so think of, in here I just drew hexane. If you have hexane, several hexanes, if they're linear, they will have a higher interaction surface. In other words, they can pack better. Okay, so the more linear it is, the better the packing, if you will. So it means that they interact more strongly, so the higher the boiling point. If instead of hexane you have something like that, it still has 6 carbons, but this will be higher more difficult to pack, and therefore if it is more branched, it will have a lower boiling point. All right, so let's just finally run a little bit of a problem solving and see if we can figure out or we can answer some questions. Okay, so in this case, we have to figure out in which case which substance will have the highest boiling point. So for A, you have bromomethane and fluoromethane. Both of them will have a dipole-dipole interaction. Okay, but if both of them have dipole-dipole interaction, you're gonna go with the major distinction. In this case, the bromine has a higher mass, therefore the H3 bromine will have a higher boiling point. You may be thinking, wait a minute, how about the extent of the dipole? And you would be true. Okay, it's also true that for a methane, the dipole is larger. So this is why these kind of problems are hard to tell, because you could say that because fluoromethane has a larger dipole, that may override the factor of mass. I would agree with you, and this is why I don't like these kind of problems, because they try to simplify something that after all it's more complicated than that. And you will see many exceptions, as you have seen in the past. So stick with me. We're going to choose this one because mass is more important. So when you have similar types of interaction, you're going to go with the distinctive factor, which in this case is mass. Now, this is a very different case. In here, magnesium chloride is ionic, while phosphorus chloride is not, is molecular. So because this one is ionic, it will always have a larger boiling point than the molecular solid. Finally, so C, you have, this is propanol, and this is ethane, methane, ether. This, for propanol, you have hydrogen bonds, while for ether you only have a dipole-dipole interaction. The one with hydrogen bonds, because it has stronger molecular interactions, it will have a higher boiling point. Okay, and finally we are comparing methane and propane, sorry, ethane and propane, yes. So they all both have the same kind of interactions. They both have London or dispersion forces. However, propane has the larger mass, therefore it'll have the highest boiling point. Okay, only very few specific cases, and I will tell you that this case is actually problematic, but in only a few specific cases you will be able to tell which one is the substance with the highest boiling point.